just gonna check that out. Where are
Yeah,
we?
I can see it said the webinar is being live streamed.
Okay, let me
Should be
pull it
good
up.
to go.
There we go. Yep, we are good. We are good is on there. All right, cool.
Hey, Jessica.
You see, Scott, if you leave it to DJ, he can do all this stuff.
Did Nancy respond about Carl?
Mm-mm.
Okay.
Yeah.
All right.
Sorry.
So,
yeah.
It's not your fault.
Steve,
I know I got a message from you and from Carl to do something to like find out some information. Okay, great, thanks.
So Steve is trying to join. So all these people are watching in the inside workings of the there he is. I see Steve in there.
Yeah, I've just promoted him to panelist.
All right, cool, thanks. There he is.
Yep.
Hello, Steve.
Hello.
All right. And there's Courtney. Look at this. We got a full house just in time. All right, Steve, I got just we are live, but so we're gonna keep this to a minimum, but I'm gonna give I'll start off and then Alex will go next. You'll start with the Ewok slide.
Okay.
All right, and then I'll take the end.
All right.
All right. So we're gonna so right now, just so you all know, we are streaming right now because we wanted to start early so we get Steve in. So we will give you just be go on quiet for a couple of minutes and let people hang out. All right. And we will see you all on the backside. All right. Just a heads up for everybody. We have we'll start at right at noon. Got another minute or so to go as people roll in. Thank you. You're all seeing the slide, right? Perfect. Okay. All right, and we're at 12. All right, sweet. Thank you everybody for joining in. Welcome to the April 17th, 2024 edition of the ACS Virtual Symposium. We're really excited to have two fantastic speakers today in Professor Huw Davies from Emory and Professor Courtney Roberts from University of Minnesota. In addition, we have some special guests with us today. We have, in addition to my normal co-host, Steve Silverman from Merck, we have Professor Alex Grenning and Professor Jessica Hoover from the University of Minnesota, who are also members of our virtual symposium behind the scenes committee gang. And so we're going to have a couple extra co-hosts with us today. And what I'm going to do right now is throw it over to Alex Grenning, who's going to be starting off with our intro slides.
Hey, everybody. Really great to be here with you all. I've got a couple slides to share with you. First one here is the Graduate Research Symposium that is coming up. A quick little shout out to anyone in the audience that could potentially sponsor or be a delegate from industry. We are seeking support and presentation at this event. If you need to contact someone regarding that, the names at the bottom, Angie Angelis and Andy Evans would be good contacts. Next slide, please. Okay, we have the fall ACS coming up. I think the main thing here is registration will be opening soon. We don't know exactly when, but we got a really great program put together by the DOC leadership. So please consider joining us, and registration information is coming soon. One particular symposium we want to bring attention to is, next slide.
Oh. That's next, yep.
Sorry, 2 slides forward.
Here, I'll go here. There you go.
Yes, a couple symposia that we want to bring attention to are the early and mid-career investigator symposia that are happening. This should be a really great event. If you happen to be attending the event, please see this fantastic work from some of your junior and mid-career colleagues. Okay, back one slide. Let's see, what was I supposed to say here, Scott?
Travel awards, man, for undergrads and grad
okay,
students.
we got some travel awards. Please consider applying for them. There's often this is often a really great opportunity, and we try to recognize as many people as possible. So please, if you are looking for some support, submit an application here. Okay, great. Thank you. I think that's what I have to say. I can turn the floor over to Steve now.
All right. Thanks, Alex.
So just a note about the early and mid-career, congratulations to everyone. We had selected 18 early and 15 mid-career winners. So we definitely, as Alex said, encourage you to come to those. It'll be 4 sessions. These recognize basically everybody throughout the first 25 years of their industrial or government careers. There'll be another cycle that opens late this year. Anybody who has any questions, feel free to contact Steve Wisniewski or myself. We co-chair this program. So congratulations to all the winners. I guess next slide.
Yep.
Yeah,
wow.
So something that I am, really excited about, we all are, is the 6th EWOC, Empowering Women in Organic Chemistry Conference, which is actually going to be held right here at Merck, June 20th and 21st. Really nice lineup of speakers. You can see the EWOC website and registration links are on the left. And just something that's worth a good read is the EWOC at 5 article. The URL of that is also on this slide. So take a look, and hope you'll register for that conference. We're really excited to be hosting it here at Merck. So next slide. So the 2023 National Organic Symposium is obviously over, but what we've been doing and will continue to do throughout the year is release videos of the talks. So this is one of the benefits of being a DOC member. So certainly worth the $5 for students, $20 for non-student membership. So since the last time where I had announced that we had released Carolyn Bertozzi's Roger Adams Award, we've released 3 more, with a 4th one being imminently released. So that's Professor Guangbin Dong's talk on merging CC and CH activation. Next slide. Dean Toss's talk on supramolecular hosts as enzyme mimics. David Taisivong's talk on the discovery and development of MK0616, macrocyclic peptide PCSK9 inhibitor, affectionately referred to as the largest small molecule. Definitely a good one, and imminently we'll be releasing Mary Watson's deaminative cross-coupling. So all really great talks, completely worth the watch. Definitely suggest you do that.
Yeah, it's one of the being able to access these videos is a really great benefit of the membership of the organic division. As Steve said, it's only $5 for students, $20 for non-students, and access to the videos and all the databases we have online. So really excited, really nice to have these there, and all the historic ones as well. So from all the NOSs previously, they're all in there. So join today.
And,
And
so NOS 2025 obviously is in the planning stages. It's going to be held at Rensselaer Polytech. So, really good location in terms of access from the New York area, from the New England area. Ed Fenlon is chairing that. So reach out to him with any questions. But it's already shaping up to be a really nice event. The speakers will be announced pretty soon.
right. And since we've had a lot of interest in this symposium, we've actually been contacted by the RSC of the Royal Society of Chemistry and the SCI over there in the UK for a cross-Atlantic virtual symposium. We're going to hold our first one on Tuesday, June 11th, with Professor Sarah Reisman from Caltech and Ollie Ring from AstraZeneca. Going to have hopefully continue this in the future with one academic and one industry talk about process style chemistry and enablement of new methods. And so it's really excited to bring the RSC and the SCI into our virtual collaboration here, and just showcase the cool chemistry we're doing in both at DOC and the RSC. So put this on your calendar. We'll be publicizing a bit more of it as we get closer to June 11th. And again, as always, this is us. This is the folks that put this program together. Steve, obviously, one of the founders of it, is myself, and we welcome Alex and as co-host today, and Jessica behind the scenes with Daisy, and our sponsor for many years so far, Huw Davies, who is our first speaker today, and I'm really excited to have Huw as part of our library of speakers here. Huw, if you want to go ahead and start, I will let you get in there and put your slides up. We're right on time, 12:08, and so I am really incredibly excited to have Huw here as a speaker in our session. He's been a long time treasured friend of the organic community, very active in the Division of Organic Chemistry in all kinds of roles, a fantastic mentor, and great sponsor of the CCHF, bringing industry and academics together in a multifaceted collaborative environment. Just a wonderful experience that I know Pfizer's had with them, and a lot of chemistry has come out of the CCHF, and also they're also taking care of the Zoom and everything behind the scenes here. So I thank our former host Rio and our current hosts Alan and DJ, who are in the background taking care of all the tech, and really appreciate their efforts here. Huw went to University College Cardiff for his BS, and then followed up with a PhD from the University of East Anglia. Moved to the U.S. for a postdoc at Princeton, and before he started his independent career at Wake Forest. I followed that with a move to the University of Buffalo, and now his current position at Emory University. His lab focuses on enantioselective CH activation pathways, especially rhodium carbines. And like I said, he was the founder of the CCHF and continues to pursue all kinds of groundbreaking chemistry. And really excited again to have Huw. His awards, too many to mention, but I just want to say he's a fellow of both the ACS and the RSC, and a recipient of the H.C. Brown Award for Creative Research in Synthetic Methods from the ACS and the DOC. It's my absolute pleasure to be to have Huw as a friend, and a colleague at the DOC, but also to be a speaker here and be able to hear about all the fantastic work going on right now in their lab at Emory. So Huw, take it away.
Thanks very much, Scott. And And thank you for the organizers for arranging this meeting and inviting me. It's a great honor to be part of this as a presenter rather than be more behind the scenes as part of the support team, if you like. So what I want to talk to you today is about recent advances in rhodium carbene chemistry. And one aspect of my group that may be a bit unusual is that we have been heavily involved in broad collaborative efforts. And this began with the NSF Center for Selective CH Functionalization that really allowed my group to really broadly collaborate with academics as well as with industrial partners. And that has now, as the center has sunset, we actually now have a new consortium, which is called the Catalysis Innovation Consortium, a bit broader than just CH functionalization, but catalysis in general. And the idea is bringing in the innovation from academia, connecting with the opportunities and potential great applications in industry to hopefully benefit both communities. And currently, this community consists of 41 faculty, as you can see here, covering various areas of catalysis, as well as there'll be several industrial partners connected with us as well. So when I talk about my research program, I need to start off with the acknowledgements with the group that's really very energized in their own research and in the connecting research, as well as the many collaborators that we've had. So collaborators in industry, as well as many academic collaborators, understanding predictive rules for how our chemistry works, thinking about synthetic applications, as well as thinking about how to make the chemistry sustainable going forward as well. And during the talk that you'll hear, I can't talk about everyone that's involved here, but you're going to see many connections with other groups as we progress. Okay, so the presentation is going to begin with an introduction to our area of chemistry, a special type of intermediate and a special class of chiral catalysts. And then we'll talk about the recent advances, recent applications, thinking about the pharmaceutical connections with this chemistry. We'll talk about a new classes of carbenes that we've developed, a new class of catalysts, and then finish off with a collaborative application in total synthesis. Okay, so what our group does is based on two things, really. And one of the key elements is the class of carbenes that we are involved in. And my career is rather unusual because actually my first paper as an independent professor was on this class of carbenes, what we call now the donor acceptor carbenes. So typically, carbenes before then these highly reactive carbenes tended to just have electron withdrawing groups. And the carbene is actually very electron deficient, very little back bonding from the rhodium. So incredibly electrophilic and rather unselected. And so the twist that we did was to actually add a donor group to the system to modulate that reactivity. And that's opened up many, many directions, as you'll see. The other aspect of our program is the catalyst. So we've moved very heavily into chiral catalysts. And the aspect of these catalysts is that they self-assemble into high symmetry structures. And these are some of the examples of our most recent. Some of these are actually not published. And these catalysts, our favorite these days, are bowl-shaped C4 symmetric catalysts. And you'll see more of those as I progress. And so one of the reasons why we've expanded into so many catalysts is that our goal is actually catalyst-controlled, these days, intermolecular CH functionalization. In other words, we all know that there's a lot of activity in CH functionalization, but the big challenge is how do you get site selectivity? Because if you've got molecules with a lot of CH bonds, it's tough to control that selectivity. And of course, one tactic, if you're doing radical or photoredox chemistry, you're often relying on inherent selectivity in the molecule. There's a particular CH bond is preferred. And another, of course, major tactic is to use directing groups. So a metal will coordinate to those directing groups, place it in close proximity to a particular CH bond. But what we're interested in, as well as several others, is the idea of getting catalyst control without any particular feature of the molecule that's deliberately set up to allow a selective reaction to occur. And we're approaching it, of course, with our donor acceptor carbines, which have the opportunity to be highly selective. And of course, there are various other strategies, and I've listed some of the key players in this particular slide. And so our controlling elements come from three components. Initially, we focus very much on how can we make the catalyst cause the environment just by the carbine to be very crowded to modify the selectivity. More recently, we're focusing on these bowl-shaped catalysts and using the catalyst wall to control it. And we've had some really surprising results, how the steric influence of the acceptor group can actually have a dramatic influence as well. Okay, so the way we do CH functionalization is in the following manner. We start off with catalysts that are actually perfectly stable. They're stable to moisture for years, stable to air, no problem. But they're incredibly reactive when in the presence of diazo compounds, where basically it results in a nitrogen exclusion and generation as a byproduct, of course, this carbene. And because nitrogen is so stable as a byproduct, we have a very reactive transient metal carbene. And even with the donor group, it's still electrophilic enough that it can start to abstract the hydride from even an alkane. So it begins to abstract the hydride. And before that is complete, you're building up positive charge on this carbon. The carbene will actually insert into that CH bond, generating your product and regenerating the catalyst. So this is a very effective catalytic cycle. And the fundamental type of things that we've been able to do is take totally unactivated CH bonds, which normally one would have thought would be very difficult to distinguish which CH bond would be functionalized. That's why they're all in gray. But basically, you have catalysts of different steric environment that can go electronically. The tertiary site is preferred. So this catalyst in blue is actually one of our less crowded catalysts. So it gives selective reactions at the most accessible tertiary site. This catalyst here is more crowded, so it will do a selective reaction at the most accessible secondary site. The tertiary sites are now not accessible. And it will distinguish hitting this C2 carbon instead of the C3. So it's very subtle in its control. And this is one of our most crowded catalysts, and this will do a selective reaction at a primary site, again, overwhelming the electronic preference. And more recently, we're interested in these bowl-shaped catalysts. So here's an example of one of the bowl-shaped catalysts, because what that will do is distinguish between hydrogens where electronically and sterically, one wouldn't have expected much difference. So the C3, C4, C5 equatorial hydrogens of an alkyl cyclohexanes are very, very similar, but we can get a clean reaction at C3, which is controlled by how this molecule fits into the bowl. So there's an element of thinking about it like an enzyme, except we're using a high symmetry enzyme to achieve these types of reactions. So that's the basic fundamental component of our group, these donor acceptor carbines, and then these designed high symmetry catalysts. And so what I want to illustrate to you is what we've been doing very recently in this area. And we've really been focusing on how can we make this pharmaceutically relevant. For years, I've talked at pharmaceutical companies, and they've all listened politely, thinking there's absolutely no way we will use this chemistry involving highly reactive diazo compounds and really expensive rhodium. So how are we going to change that viewpoint? I'll then describe these new classes of donor acceptor carbines because they've resulted in a really interesting twist. And then we've got an even higher symmetry catalyst. And so now a D4 symmetric catalyst. So I'll illustrate how that is developing. And then we'll highlight this total synthesis at the end. Okay, so in terms of applications, the type of things my group likes to do, and this is a paper that's just coming out now, is to take basically do rapid constructions of chiral complex structures. And so one example was we were interested whether we could take a paracyclophane and be able to do selective. We were thinking about CH functionalization or derivatization of it in some way. And what we find is that we can actually do a very nice reaction where we can actually do a desymmetrization and generate products of this type in high yield with very high enantioselectivity. And if you're interested, you can do a second reaction either with the same diazo, which actually makes a meso compound, so that's not so excited, or with another one to add further derivatization to the structure. And the reason why I mentioned this one is because the chemistry actually relies on this bowl-shaped catalyst. So it turns out when we're doing normally, a 1,4-disubstituted benzene ring is actually sterically protected from the carbene, and so you will tend to get CH functionalization to occur. But paracyclophane is a famous compound that's sterically constrained, and so we have a situation, even though it should have been sterically protected, we can actually functionalize the benzene ring. And so there's two sites of cyclopropanation, the one I've drawn here, which actually would put the group in a bad position, or we could cyclopropanate the other double bond. And it turns out we've got very good catalyst control here. So for example, in the regular structure, obviously this part of the molecule is interfering with the wall of the catalyst. So we find if we use a very small catalyst like rhodium benzoate, it will tend to form this type of product. But if you use a bulky catalyst, it actually prefers to form reaction at this double bond to avoid that steric constraint. But these bowl-shaped catalysts, which sort of look bulky, actually aren't terribly bulky at the carbene site. And what happens here is that actually this is the bad structure because the grouping now is banging into the wall of the catalyst. And so consequently, this catalyst behaves as if it's a really small catalyst, does a reaction through this orientation, leading to the observed products. So again, it's an example of how we're using the bowl to control the chemistry. However, when we're thinking about applications, we often like to think about applications that have pharmaceutical relevance and how can we quickly access sort of novel chiral scaffolds. So from very simple compounds. So we showed we could take silocyclobutanes and do a very nice CH functionalization. We can do the same with these bicyclopentane derivatives. We can do reactions with cyclobutane derivative. We can actually control whether it's going to attack C1, as I've drawn here, or C4. We've done a lot of work around piperidine derivatives, trying to get C2, C3, or C4 functionalization, depending on the catalyst. And these are all collaborative projects that involve companies connected to these as well. And what we find in the consortium, it's exciting to have discussions with industrial partners because it actually leads to interesting synthetic challenges. Some, ideally, some that our chemistry can't do at the moment. So it forces us to expand the methodology and expand the catalyst design. Now, one of the issues, of course, that's fine to work with industry, but, you know, is the chemistry practical for them to really do something useful? So one of the things we have to deal with is the rhodium being so expensive. We've looked at other metals and still the dirhodium is the best. So for us to make our chemistry practical, we've really got to focus on high turnover catalysis. And so we collaborated with Donna Blackman to study the kinetics of the system, and then showed that routinely this chemistry can be carried out with 0.001 mole% of catalyst. And also demonstrated that a system that BMS had explored with one of our early generation catalysts with a 0.2 mole% catalyst loading, we showed using our new system, it could operate also on the 0.001 mole% and give very high enantioselectivity. So beyond the cyclopropanation, we wanted to achieve high turnover in the CH functionalization, but that is much more challenging because the rhodium carbene structure is prone to destroying the catalyst unless it's trapped quickly. And of course, the CH bond reaction is harder to do. But we took on this challenge, and actually the basic catalysts that were developed here did not work out. But in the end, actually, it's the bowl-shaped catalysts that are the winners here again. We were able to develop a system that could actually do CH functionalization with a catalyst loading of 0.0005 mole%. And basically, you can follow these reactions by react-IR, and this is what this graph is showing, how this reaction can be completed with that low catalyst loading, doing a roughly 200,000 turnovers in just 2 minutes. And so this is the way we're dealing with sustainability, going with incredibly low catalyst loading to make the process more viable. And just to illustrate the point, we've had a collaboration, a paper that just came out with Eli Lilly, where there's a great interest in this very small scaffold, which is present in many drug systems, as you can see here. And the obvious way to make this is through a simple cyclopropionation with just an acceptor carbene. However, that is not a practical process. There's a much longer steps needed to make this compound. And the reason why is the reaction can't be carried out with any reasonable catalyst loading. And so we decided we would take what we've learned about donor acceptor carbenes and to apply it to this system. And I won't go into the details, but we found we could do the reaction on 0.005 mole percent, about 200 times less than what was known before. And also demonstrated you could get into either diastereomeric series without chromatography on gram scale, so very practical for scale-up. And indeed, when we were set to publish this, there's actually a patent application associated with this, because under these low catalyst loading, this is now a very practical process, unlike what was available before. The other aspect that's really important is the diazo compound. This is actually the most important aspect, because diazo compounds, even though the ones we work with are easy to handle, they are potentially explosive, so you don't want to make a lot of them. And so the big aspect is to do the chemistry in flow. So we've been applying how we can make these donor acceptor carbenes in flow. We worked with Shannon Stahl on a collaboration to show you could do this transfer using copper catalyst and just air as a terminal oxidant to make the diazo. The reason we wanted to develop this process is we didn't want any byproduct or just water as a byproduct to avoid having to do an inline extraction. We then showed that this could be done in flow. We collaborated with Chris Jones. This is our solution. Chris Jones is a chemical engineer, so this is very unsatisfactory for him. So we basically have just got a cartridge with copper acetate there. We add the hydrazone on the top, and you can see the yellow color here because this is the diazo going straight into the reaction, so no isolation needed. And then he developed a more sophisticated system where basically you use bring in air as the terminal oxidant, and again the process works very nicely. So this is definitely the more industrial type approach to achieve these reactions. And actually, we've developed another approach with AbbVie because they were interested in these type of compounds as potential drug candidates for cystic fibrosis, and they needed to scale up the chemistry. And actually, we collaborated with them not on actually running the flow reaction, which they demonstrated could be done on a 100-gram scale, but in terms of developing the catalyst and some subtle aspects of the reaction conditions that were required for this successful reaction. Now, I should mention, sorry, one thing I want to mention, during this process, we found that HFIP was a wonderful material to actually block subtle effects of traces of water on this chemistry. So basically it blocked having water as a poison in this reaction. And so after completing this project, we actually went into a collaborative project with Novartis to see whether HFIP could be used as a universal protectant against all this classic poisons you have in carbene chemistry. In other words, if you have many nucleophilic heterocycles of pharmaceutical interest, or OH bonds or NH bonds, they will tend to react very easily with the carbene. So you would get these as side reactions rather than the desired, say, cyclopropionation or CH functionalization. So we became interested whether the simple trick of adding HFIP to the reaction would actually limit how these poisons would interfere. And actually, my student, Jack Sharland, actually went to Novartis to do some high throughput experimentation around that. And basically what he did was he examined a range of poisons. Basically, we're running a standard cyclopropionation reaction and seeing if you add a poison, does it interfere with the reaction? And he looked at three conditions. The blue would be ones that work without the need for HFIP. The green would be the optimum catalyst to work with 10 equivalents of HFIP. And the orange would be what would work when HFIP was solvent. And then the gray we don't want to talk about because those are the reactions that still wouldn't work in the presence of the poisons. And this is a very quick summary of what he found. Aromatic heterocycles, blue, very few of them would work without HFIP. They all work with addition of HFIP. Same with nitrogen nucleophiles, reactive OH bonds, and even a whole range of reactive NH bonds. Only a few examples now will poison the reaction in the presence of HFIP. And just to illustrate the sort of potential of this, you can take substrates that no one in the past would tend to think about doing cyclopropionation on because all of the nucleophilic sites or the OH sites would interfere. But now, as you can see, they all can be carried out effectively in the presence of HFIP. Okay, so that illustrates how we're working tightly with industry. We actually have several active collaborations. Some of them now focus on IP issues, so we can't really discuss at this stage. But the chemistry now has reached a stage where it is viable for industry to be thinking seriously about the new opportunities that come from this type of synthesis. Now, every project has got limitations, and our limitation, of course, is that we need to use donor acceptor carbines, and that's great if it fits your molecule, but if not, then it's a problem. So this is our standard established system, and so we're exploring what type of other new carbine systems could we do to broaden the scope of this chemistry. And I'm just going to very quickly talk about two, and this looks like sort of a pretty obvious extension, but there's been some really big surprises. So using a phosphonate or using a ketone. And so just to illustrate, the catalysts that work well here is again those bowl-shaped catalysts. So this is one particular one. And this is not the best catalyst for high EE with the standard ester as the acceptor group, but they're just showing this as a point of reference, how this system is not, even though it's a big catalyst from a structure point, it's not sterically demanding at the carbene, so it still prefers the tertiary site. However, if you use that catalyst with the phosphonate, the reaction goes exclusively, and this is the optimum catalyst for the phosphonate, you can see it goes exclusively for the primary site with very high enantioselectivity. And just to illustrate, here are some variable substrates, just to illustrate there is functional group compatibility in here for this primary benzylic CH functionalization. The other one I want to talk to you is this diazoketone, okay? And again, it's a bowl-shaped catalyst, it's the winner here. And again, illustrate the comparison with three sort of representative substrates. What you typically can do with the aryl diazoacetate system. Again, this is not the optimum catalyst for high EE in this reaction, but you can see it's respectable and you get reasonable site selectivity, reasonable diastereoselectivity, at least in the first two, not so good with this third substrate. In contrast, when you use the ketones, the reaction goes off scale. And I mean, I'll only read the first one. You can see the site selectivity is perfect for the C3 position, desymmetrizing this molecule, exceptionally high diastereoselectivity, and greater than 99% EE. So incredibly high values, as you can see, compared to our traditional chemistry. And this illustrates a variety of the type of substrates that can be carried out, again, with very high enantioselectivity. And again, so this paper's just come out in JACC, so I'm not going to go into detail on it. You can also do a lot of interesting further applications on the initial product. And many of these reactions are also highly stereoselective. So you can add additional stereocenters to your molecule going forward from the initial system, which is essentially a single enantiomer, single diastereomer. Now, all of our work, we work very closely with various computational chemists. With this one, we work very closely with Jamal Mosaiev, and we learned something really exciting for why this is performing so well. So typically, when you're thinking about asymmetric induction, you're really focusing on, which face of the carbene is going to be attacked. But there's a really interesting feature with the acceptor group in this system, because it relies orthogonally, more like I've drawn here, than to the rhodium carbene structure. So in other words, you've got an alkoxy pointing one way and a ketone pointing the other way. And we showed in 2022 that even though you can get attack from both sides, so now it depends on the chiral influence, which enantiomer you're going to get, there is a difference which side is attacked. The thing that's interesting about when you have these aryl ketones, then it turns out only one side can be attacked, and that is on the side of the carbonyl. In other words, once you made the rhodium carbene, the phase selectivity is already predetermined by the carbene structure, not the rest of the chiral influence. And this is a very important new concept in terms of asymmetric catalysis in this area. So what I'm showing to you is how the carbene fits into this pocket. And so in this particular structure, you can see that this is the aryl of that aryl ketone, there's the carbonyl. So this structure has to be approached from the ketone side. So it really depends, is this structure preferred over this one? Because whichever one is preferred, it will attack on the side of the carbonyl. So this is going to be a very important for future ramifications in terms of understanding asymmetric catalysis in carbene reactions. Now, let me quickly talk to you about some of our new catalysts. So as I said, we rely on this self-assembly to generate high symmetry catalysts. And we actually proposed now back in 1996, when we developed our first chiral catalysts, to try to explain why they were working. We suggested that if you have a big group on each carboxylate, then they will self-assemble. And you have an interesting issue because that group will either be pointing upwards or downwards from the dirhodium. It can't exist in the periphery of the catalyst. And that leads to high symmetry possibilities. It could be C2 symmetry if it was up, up, down, down. If it was up, down, it'd be D2 symmetric. If it was all up, it'd be C4 symmetric or an alternative C2 symmetric. So that was just a concept, actually, to get this paper published. They asked for us to explain what could possibly be going on. And it turns out this concept is actually now behind all of the catalysts that have been developed by us and many other groups since then. And so the catalyst we tend to focus on these days is these C4 symmetric catalysts. But that means the two faces of the rhodium are different. So we have to block the bottom face of these rhodium catalysts. So we became interested whether we could get D4 symmetric catalysts where both faces would be the same. And so the way we thought of doing this, and it's in the literature, is to use binaphthyl C2 symmetric binaphthyl phosphates. And we expected these to be locked, so they would have to be D4 symmetric. But it turns out a lot of people have worked with these binaphthyl phosphates and they haven't been terribly successful. In other words, they give you some in anti-selectivity. Definitely the parent has been shown to be D4 symmetric, but you can see the enantioselectivity is rather low. And so we've actually developed a new catalyst that we've stopped trying to name our catalysts somewhat related to their structures because they got too cumbersome. So we call this just mega BNP. And so this is our new catalyst, and let me show you how this came about. So when we were looking at the binaphthyl phosphates, they are very interesting. The parent one is definitely D4 symmetric, but you have an issue. Then the groups aren't sticking out too much away from the surface of the catalyst. So we decided we needed to make the structure bigger, but you can't approach it the way most people make these more effective, which is to functionalize C2, because you can see C2 would interfere with the adjacent ligand. C6 is too far away. So we really focused on C4. And so we prepared a series of, now it's very difficult to make just the C4. So we made the catalysts that were substituted at C4 and C6. And what we decided to do was to explore really large aryl substituents. And what we found, as expected, the parent gives you moderate EE. The tetraphenyl catalyst had been made previously and gives moderate EE. But if you go to bigger groups, you can get higher in anti-selectivity. So to go further forward, we wanted to understand what was the issue with the phenyl? Why didn't it do better than that? And so we got an X-ray structure of the phenyl, and you can see it's pretty complicated. It turns out there are 4 unit cells in 4 catalyst structures in the unit cell. And what's even more disappointing is that they're not high symmetry structures. Well, the one on the left is C2 symmetric, but the other others aren't high symmetric because actually there's a lot of phenyl-phenyl interactions occurring, breaking the symmetry. And so that led us to think, well, we need to further refine this. And what we decided to do was actually to try to keep this grouping the same, so have 2 chlorines here. We developed a nice synthetic way that we could do this, and just modify the aryl group. And the plan was to make a lot of them, okay, using this chemistry, but we only made 2. And you might say, why did you only make 2? Well, the reason why is because we hit the home run on the second one. So the second one, which is a 3,5 ditertiary butyl phenyl, actually gives 99% EE in this reaction. And it's interesting to compare. So if you look at the tertiary butyl phenyl, what do you find? It is more high symmetry now, but it's not D4 symmetric. It's actually C4 symmetric because the 2 rings do interact with each other. And so it basically is not a perfect, the 2 faces are still different. But the interesting thing when you look at the 3,5 ditertiary butyl, it is a perfect D4 symmetric structure. And so with this catalyst, we've taken on some of our best carboxylate catalysts. So this is the example of the challenging getting C2 selective reaction. And what we find with our new catalyst is not better. You can see we do prefer C2 selectivity, but the still 96% EE, but it's not as good as we see with our best carboxylate. But it turns out when it came to the tertiary selective catalyst, so this is a competition between a tertiary CH bond and a nicely accessible secondary CH bond, where this rhodium tetrachloropetade is our best one that does pretty well for C2. But this new catalyst outperforms it, gives higher enantioselectivity and higher site selectivity. And so just to illustrate very quickly the type of reactions we can have, you can do reactions on alkanes and get pretty decent site selectivity. And also you can do the chemistry in the presence of various functional groups. This is just a small subset of what we've been able to achieve. Okay, I know my time is running out, so I just want to finish off very quickly to tell you about the impact on synthetic strategy. And so what's great, and I'm a methodology person. We've done some total synthesis ourselves, but we're not a total synthesis group per se. And there's a different mindset between a methodology group and a total synthesis group. And so it's great having conversations in these centers between the 2 groups to see what you can do together. And so over the years, we've collaborated with Jin Kuan Yu to do, we like to do sequential CH functionalization. So we worked very nicely with him, where we used our carbene chemistry followed by his directed CH functionalization. We also collaborated with Ken Itami from Japan, who developed a nice way for C3 functionalizations of pyrols. We combine it with our CH functionalization to quickly complete the synthesis of dictyodendrin. This was a fun project because it was done in 7 months, where his student came to my lab for 3 months, and then my student went to Japan for 4 months. And then we've also worked with Eric Sorensen, who proposed ridiculous things for our chemistry to do, which were impossible. We did counter proposals and then found some common ground. And this implies our selective CH functionalization, again, combined with Jin Kuan Yu's directed CH functionalization HEC reaction. So that's great, putting 2 reactions together, but the center always wanted to go for something really big. And so I want to finish off with what we think of our signature total synthesis coming out of the center, which is this synthesis of cylindrocyclophane. enabled by sequential CH functionalization. So this is the compound. And it's really interesting the way this came about. Basically, Brian Stoltz sent me an email when we said we could selectively functionalize at C2 and suggested, if you can do C2 functionalization and control the stereochemistry, you'd be able to make these two centers here. And based on that initial sort of idea, and we wanted to go crazy in terms of CH functionalization, we thought, could we make the whole molecule using these type of retrosynthetic analysis where we're going to do many, many CH bonds? Now, I can see that Scott is getting a bit worried, so I need to go through this super, super quickly. And what I would encourage you to focus on the colored circles, because those are the CH bonds we're going to functionalize. So we needed to start off with a reaction where we're going to do an asymmetric selective CH functionalization at a primary site. We had to use one of our crowded catalysts, so we got this in 97% EE. Then the way we actually make the diazo compounds is formally a palladium catalyzed CH functionalization reaction as well. And then the next step is the big one. We want this carbene to find this CH bond. And it turns out it works really well. It goes with very high site selectivity, diastereoselectivity, and respectable enantioselectivity, making those two chiral centers that we needed. We then needed to follow up with another palladium catalyzed CH functionalization to generate our carbene precursor. And now this is the next big one, where this carbene has to find this CH bond. And it turns out that works beautifully. Again, we use one of our special bulky catalysts. And what's interesting about this, we're operating under Horrow's effect. So in other words, the diastereoselectivity is lower, but the enantioselectivity is perfect because the bad diastereomer from the last reaction, bad enantiomer from the last reaction is now producing a diastereomer in this second reaction. And then we take advantage of the different protecting groups we have on the acids to get the diacid converted to the Weinreim amide. We hydrolyze the other two acids. Then we do a photochemical reaction to generate this acetoxy group. And this is why now we see why Jin Kuan Yu is involved here, because now we need to do a tetrafold directed CH functionalization to generate a compound like this. And basically, all of these steps were carried out with help from Brian Stoltz and advice from Jin Kuan Yu, basically in my lab. But then we got stuck, okay? So we made about 300 milligrams of this and actually supplied that to Brian Stoltz's group because we would have wasted it probably in 5 reactions. And they went, this was actually very, very challenging to complete this. But basically, we thought the acetates would help to make the chemistry easier, but it turns out you really had to go back to the methoxy group finally to work through this end game sequence. There's a really massive effort by them to get this to reach completion. But they have completed this. Liam Hunt and Camila Suarez were the 2 key players who finished the end game. Aaron Bossi was the one who was working in my lab in this program. So basically, the synthesis is completed after a real tour de force. And so where are we going future directions? We still got a lot of selective, more selective reactions we hope to get through CH functionalization. We're very much focusing on the applications these days. We like the pharmaceutical projects, increasing the sustainability of the chemistry, still thinking about how to use it in total synthesis. And we also have a lot of drug discovery programs, either collaboratively with industry or collaboratively with the medical school here at Emory. Definitely the mechanistic understanding is crucial. The chemistry is really certain. Jamal Mozayev has been a fantastic partner, but we're working very closely with other other computational collaborators as well. And we think the whole chemistry is ideally suited for application for predictive modeling, thinking about really maximizing high throughput experimentation and machine learning in this program. Okay, finally, I want to thank the group and definitely the 2 centers that I've been associated with. My students have been wonderful because not only are they driving their own projects very well, but they are the links with our collaborators to make all these collaborations work as well. And finally, thank you very much for your attention, for joining this, and for Scott not getting too mad that I'm a few minutes late.
No, you're all right, Huw. I will. We are gonna ask you, there's a question from Professor Chapini down from UNC Wilmington online. I'm going to ask you to answer that online if you can, because I think it's about time we got to move on to Courtney. But I want to say thank you again for everything you presented, for your presentation today, and everything you do for the community and the DOC. It's been a pleasure. Thank you, sir, and appreciate you being on our show today. So I'm going to let you answer the questions online. I'm going to throw it over to Alex, who's going to introduce Courtney Roberts from the University of Minnesota.
Okay, hi everybody. While Courtney is pulling up her slides and while Huw is putting his away, I will introduce our next speaker. It is a pleasure to introduce Courtney Roberts, someone I've known since the start of her career and have followed it closely, and am now currently following it much closer as her colleague. She started at the University of Minnesota in 2019. Prior to that, she was at Pepperdine University, at UNC for her PhD, and at the University of Michigan for her postdoctoral studies. She worked with Professor Meek and Professor Melanie Sanford, respectively, at those two final places. Her research and interests are broad. She has a multitude of publications already, ranging from chemical education to early transition metal catalysis and into transition metal catalyzed reactions for arine generation and reactivity, which I believe is what we're going to hear about today. She has been recognized quite a bit for her science, including awards and grants and other recognition. A couple examples would be the Amgen Young Investigator Award, TEMA Journal Award, NSF Career Award, and the NIH Mira Award. A couple fun facts about Courtney, just two of them really quickly before I turn it over to her. One, of course, I think she's proud of all of her academic institutions, but her office is indeed strongly accented baby blue. So shout out to any Tar Heels fans in the audience. Secondly, Courtney is very cool, and I like to associate myself with that coolness. Not only is she just a wonderful colleague and really funny and just great to be with. Again, I like to associate it with it because we live in the same cool neighborhood. So anyway, if she's not on campus, you might find her in Northeast Minneapolis, enjoying one of our James Beard Award-winning restaurants, coffee shops, breweries, or cocktail lounges. Okay, with that being said, I will turn the floor over now to Courtney. Courtney, thanks for joining us today.
All right. Thank you, Alex, for that introduction. It is wonderful, as you all are probably very jealous that I get to have Alex as a colleague these days and a neighbor. So that's really fantastic. So are my slides up? Everyone can see that all right? Okay, awesome. Let me switch over to a laser pointer here. All right. Well, I'm absolutely delighted to be here. I want to thank whoever nominated me and the committee for allowing me to have this incredible opportunity. It was very inspiring to see all the wonderful carbene chemistry. I am a huge fan of reactive intermediates, and so you'll see a lot of those today with a focus on a lot of arine chemistry. So as Alex said, we work in a lot of different areas, but I wanted to first take a shout out for my group. They're really fantastic. They work hard, they work smart, they work together, and I'm incredibly grateful for all that they've done over my almost 5-year career here at the University of Minnesota. We started during a pretty challenging time, and I'm always going to be grateful for this cohort of students that has gotten us through to the end of tenure. So I'd also like to really acknowledge and thank the funding sources, because we wouldn't be able to do the type of chemistry that we do without them. So as Alex said, we work in a lot of different areas, and we would be here all day if I tried to talk about all of them. So I've just chosen one story, but I did want to introduce that we do a little bit of photoredox catalysis, really thinking about sustainability and if we can have our electron donors and acceptors in the same molecule. As Alex also mentioned, we do a lot of chemistry with early transition metals. If you don't know, metals like scandium and yttrium in group 3 are as abundant as metals as, like nickel. And so we've been able to show a lot of actually redox chemistry with early transition metals, which might be surprising, but we incorporate redox active ligands into the catalyst. And so we've done a number of cross-coupling, and we're actually moving into the CH activation realm because early transition metals can undergo CH activation through a pretty unique sigma bond metathesis mechanism. So you'll see some forthcoming CH activation from our group. But really what I'm going to focus on today is this project about how metals can have a lot of synergistic chemistry when they're bound to arines. So we work in a number of different areas of arine chemistry, including generation of new arine reagents. We work a lot on the regioselectivity challenges that come with arines. As you can imagine, an arine has two termini of a triple bond that you could react with. But really what I'm going to focus on today is this story, which will be coming out very shortly, about some N-heterocyclic arines. So, as organic chemists, I think we can all really appreciate how much heterocycles actually impact our daily lives. And this comes through pharmaceuticals as well as the agrochemicals that we use. Living in the Midwest, there's a lot of focus on agrochemistry. And as we look at, a number of scaffolds, you see this a lot on organic chemist slides. What I really want to point out to you, though, is we have a lot of N-heterocyclic scaffolds that have this 1,2 disubstitution pattern with them. So that can be two carbon-carbon bonds next to each other, as we have an ambient and Lipitor. We can think also about some carbon heteroatom bonds, again in that 1,2 disubstitution pattern. We can start to think of, annulated molecules as, having to make those bonds through this 1,2 disubstitution pattern. So it's a quite critical motif in pharmaceuticals and agrochemicals. And if you don't work with heterocycles, you might not know that they're incredibly challenging to make. And so if we could think about new retrosynthetic disconnections for heterocycle chemistry, it has a lot of value in the synthetic community. So one intermediate that we really like is arines, right? And so if we were to kind of deconstruct these molecules, I just finished up teaching a lecture for sophomore organic, and I teach a lot of retrosynthesis. And, when we're thinking about retrosynthesis, an arine intermediate is actually, kind of the perfect candidate for us to think about having a 1,2 disubstitution in a single pot, right? So we can think about the sustainability aspects of that. We really don't need to worry too much about having multiple reactions. We can just do this one step, one pot. So when you're thinking about arine reactivity, we're thinking a lot about electrophilic reactivity. So you might have some nucleophilic synthon, maybe an organometallic reagent, reacts at the first termini. That places a negative charge on our arine ring, which can react with an electrophilic synthon. Right, we can think about alkyl bromides or halides of any sort. These would be great candidates, right? So as you start to build up these molecules, you can see how useful it would be if we can access arine intermediates, right? Not only do we think of carbon-carbon bonds, but arines also react readily with carbon to make carbon heteroatom bonds as well. Arines, again, engage in a lot of 4+2 cycle additions and pericyclic reactions. So, hopefully you can start to see that this is a quite interesting and potentially transformative retrosynthetic analysis. So, thinking about arines, they're very highly reactive. Do people use these in synthesis? The answer is yes, all the time. So here's just a few selected examples from a really fantastic and comprehensive review coming out of the Stoltz group. And it might be challenging to see where our arines came from in these molecules, so I'll just walk you through a couple of examples. So in this example of ellipticene, this alkaloid, we see that an N-heterocyclic arine engages in a 4+2 cycle addition with this furan. And after a number of synthetic steps, we get to this, annulated product here for ellipticene. Actually, multiple people back in the 80s were thinking about using 3,4-pyridine as an intermediate here. We can turn over to actually making heterocycles through arines, and this really beautiful example from the Stoltz group, which they actually construct the benzofuran core through reacting this lithiated alkoxide with an arine intermediate. One of my favorite examples comes from Neil Garg's lab, in which they actually carry an arine, a masked arine precursor throughout the entire synthesis, and they're able to do a 4+2 cycle addition at the very end, and then start to actually functionalize a lot of the products that they get and derivatize these natural products so they can test a lot of different properties of them. So you see this is a highly decorated molecule. There's a lot of functionality, but we can still use arine intermediates, specifically, N-heterocyclic arine intermediates in these examples. So if you're unfamiliar, you really haven't thought about arine chemistry for a while, we typically take something like a strong base with a leaving group alpha to it, and we deprotonate and that leaving group leaves. We can also think about doing this a little bit milder conditions with Kobayashi arine precursors. These TMS triflates can be activated with fluoride, and again, we have a triflate as a leaving group. So this reacts quite well. We form these arines, these very reactive intermediates. And so, what I would say is probably my very favorite collaboration between a computational group as well as a experimental group comes from the Garg, Hauk, and Patton labs. And what they did is they actually predicted whether we can use an arine or not, whether we can make it. So what I've shown you, of course, is successful predictions and successful molecules that have been made through arine intermediates. But it turns out that if we need a model to predict the synthetic utility, that means we can't actually make all N-heterocyclic arines. So let me walk you through what these two groups or these three groups have come up as what they classify as accessible arines, meaning we can access them energetically, we can use them in synthesis. So 4,5 indoline works quite well. I showed you that Garg example. We can also think about 3,4 pyridine, another N-heterocyclic arine working quite well. It engaged in a 4+2 cycle addition to generate elliptosine. Right, so we can see highly successful examples of N-heterocyclic arines in synthesis. When we take a look at 4,5 indoline, we can actually move that triple bonds over to the 5,6 position or the 6,7 position. It works quite well, and these have been used and synthesized, experimentally verified. I'm going to come back to this benzothiophene example in just a second here. But why this paper is so useful to the synthetic community is it says we can access this class of arines, energetically accessible, experimentally verified. But unfortunately, there's an entire class of N-heterocyclic arines that are inaccessible. The energy for that dehydrogenation is so great. The products would be just too unstable if they were formed. As you can imagine, how much strain would build up in that at that 3,4 carbon. We were thinking about an alkyne like hybridization, SP. We want to be 180 degrees, but we see it's locked into that 5-membered ring. And so these are energetically inaccessible. We cannot form any of these arines. And it really doesn't matter, if we change the identity of the electronics of the arine, we can go from indole, we can calculate something like 7 aza-indole, and we see the electronics of that pyridine ring have no impact whatsoever. We still can't form these. You could really, change fundamentally the core of the heterocycle, going from something like 7 aza-indole to an imidazopyridine core. Again, this just does not work whatsoever. We cannot form this arine. Nobody has formed it before, and synthetically, it's just inaccessible. It's not an option for us to use as an intermediate. Benzofuran also is calculated to be inaccessible, and looking over benzothiophene might actually look pretty similar, but of course we know that sulfur is much larger, so the sulfur carbon bonds are much longer. So that's why, in fact, it's hypothesized we can access benzothiophene, the arine at the 2,3 position, but when we move to an oxygen smaller heteroatom, that's why we can't make this. And I actually think this is quite an interesting challenge because it turns out that benzofuran was actually predicted the first time in literature that an arine was actually invoked back in 1902. We often think about arine chemistry coming out maybe in the 50s or so, having sort of a birth there, but actually it turns out people have been thinking about arine intermediates for a lot longer. So, this is computed to be an inaccessible arine, and later on in the literature, it's refuted that, in 1902, what they predicted was going through this benzofuran arine was in fact not. But it gives us something to think about for, over 120 years, people have sought these intermediates as being, potentially highly useful. So going back to my retrosynthetic analysis, actually, this turns out to be a pretty terrible retrosynthetic analysis, right? I've chosen all of these N-heterocyclic arines that we cannot make, right? They're energetically accessible. I believe the computations, nobody has made them experimentally. And that's really unfortunate because we could think about how instrumental they would be in synthesis if we could get our hands on this functional group. And so that was sort of our motivation. We thought these were important enough to study and to actually have access to, that while, you know, the computations say we can't access these, we were quite curious if we actually could by sort of thinking outside of the box. So the next slide here is going to be a bit of an abrupt change from the motivation. I'm going to walk you through a little bit of a teaching slide. So we're an organometallics group, and so we love organometallic chemistry and the effects that metals have on various ligands. So this is isosol. It's a well-studied platinum ethylene complex. So we're just going to use it as a case study about what happens when a metal binds to a pi component. So what we first see and often recognize and think about the interactions between metals to ligand is some sort of electron density from our ligand being donated into our metal, right? This is a well-known phenomenon. We could think of phosphines, amines, all sorts of donor ligands do this. And when we're thinking about pi components, though, we also need to consider a second interaction that is operative. And this is when your d orbitals, they have electrons and they actually match up phases quite well with pi star CC bonds. And so what we see is that our metal is actually donating from the d orbital into this empty CC pi star orbital. And of course, as soon as we start to add electron density into a pi star orbital, you know, we have some phenomenon that start going on there, such as, you know, breaking of bonds. And so this is what is called sort of the Duhrchat-Duncanson model or the metallocyclopropane model. These are two extremes, and actual metal complexes really kind of end up somewhere in the middle. But really, when we're thinking about late transition metals, which we're going to be talking about in this talk, we're often thinking about the Duhrchat-Duncanson model. All right, so weak back donation, and that ethylene it's near CsP2 hybridized, but it's elongated a little bit. So the bond order, instead of being exactly 2 in that pi component, it gets elongated, and maybe the bond order is 1.7 or 1.8. So it's a small amount of back donation that's breaking that double bond a small amount. So this is ethylene. How does that relate to arynes? Well, you can imagine arynes have pi components, and when they bind to a metal, we can potentially see if this phenomenon is going on as well. So we can take a look at the computed value of an aryne triple bond, comparing that to that of benzene, and when we bind a metal, we do in fact see that the Duhrchat-Duncanson model is in play. And how we can tell that there's back donation into that aryne triple bond is when we compare the bond length of benzyne to that of metal-bound benzyne, we see that bond is elongated, right? So the nickel is donating back into the pi star anti-bonding orbitals, the ligand, the aryne ligand is donating in the forward direction. All of these are contributing to the elongation of that triple bond. You know, it's not so much elongated that it ends up something close to benzene, right? We still have our aryne character here when bound to a metal. It's also sort of a clue to us that we can actually alleviate some strain when we think about binding a metal to an aryne. And so you might say to yourself, well, I'm an organic chemist. I have no idea how to make that compound there. Turns out it's actually quite easy. The synthesis was developed back in the late 80s. All we do is we take an ortho boryl aryl bromide, our favorite metal of choice, for example, nickel 0 or palladium 0, our favorite phosphine of choice. It could be a monodentate phosphine, a bidentate phosphine, aryl phosphine, alkyl phosphine, you know, any sort of garden variety phosphine that you might have. And we combine those, and the nickel undergoes an oxidative addition into that metal aryl bond, right? This is the first step of, like, for example, Suzuki cross-coupling or Buchwald-Hartwig amination, right? We just do a simple oxidative addition. We're all comfortable and familiar with that. Next, we had some sort of a base or an activator, think a fluoride or an alkoxide, anything that would activate a B pin for transmetallation. Again, this is a well-known key step in something like a Suzuki cross-coupling. We can activate our B pin, and then that does an intramolecular transmetallation, and we end up with an aryne, right? So these are actually very easy intermediates to gain access to. So going back to all those, inaccessible arines that you can't actually form, we thought potentially we could access them just by using a metal, sort of thinking outside the box in terms of how to actually get our hands on these. Right, so that's that sort of central hypothesis, is that we can alleviate the strain in these triple bonds in our arines for these N heterocycles. What that would do, it would open up, I just have 4 examples here, but any 5-membered N heterocyclic arine could be accessed through this simple concept of just using back bonding to relieve that strain. So this project was spearheaded by Jenna Humke, who's a 5th-year graduate student in the lab, and she's joined by Aaron Plaszek, as well as postdoc Roman Belli, another graduate student, Sal Cargbo, as well as a former postdoc, Annabelle Ansel. So what this team did is they sort of took on this challenge. They said, you can't access these molecules, but what if we could? What if we could use this concept? So we can go back to our simple precursors, these aryl boryl bromides here. This is commercially available from everyone's favorite vendor, Ambead, pretty cheap for a heterocycle precursor. We can do an LDA deprotonation and then just quench with isopropoxy B-pen borylate. And we can access these precursors in 60% yield in a single step. We've scaled this up to over 25 grams at this point. They're very easy to access in a single step. You can imagine the wide variety of heterocycles that we can access here. We can think about changing from a 7-aza indole to a 6-aza indole, 5, 4, etc. We can think about changing the protecting group to something that's actually deprotectable, not really methyl, but something like benzyl, or even the NH. We can think about changing the heterocyclic scaffold core. These are all very easily accessible in a single step from commercially available precursors. So next, we took our 7-aza indole precursor, potentially our arine precursor. We exposed it to nickel cod and triphenylphosphine, and at room temperature over a day, we get a 65% yield of this oxidative addition complex. So at this point, everything is sort of going to plan. We can study this spectroscopically. We were ready to add in our activator for that intramolecular transmetallation. So we used a very soluble alkoxide activator here, potassium terpentoxide, and we saw no reaction. All right, so this was kind of disappointing because the literature said that, whatever phosphine you want to use, you're going to be able to do this transmetallation. But as organic metallic chemists, what we realized, actually the structure is not quite ideal for forming the arine. And that's because we need to do this transmetallation into this position that is cis to our metal aryl bonds, right? But we have our phosphine there, which means that we need to reorganize our phosphines prior to the transmetallation. The other thing that we noted is there's going to actually be probably a lot of back donation necessary to be able to actually stabilize and form these inaccessible arines. And so we likely need a richer donor than an aryl phosphine. So what we did is we took this complex here and we just added in a bidentate ligand. So we switched to alkyl phosphines. These are much more donating and so potentially stabilizing if we can form an arine. And then what we've done is we've locked these phosphines into a cis configuration, which sort of locks our sigma aryl here and our bromide, which we need to be displaced for that transmetallation. So we can do this on over a gram scale, pretty good yield over a couple of steps to get this oxidative addition complex. So we do a lot of crystallography in my lab. This is just an oxidative addition complex. Nothing really to write home about here. There's nothing strange going on with these bond lengths. This is still aromatized. It's still a double bond at that position. But really the technique that we use the most, that's easiest if crystallography is inaccessible to certain groups, is phosphine NMR. So as we know, phosphine NMR actually is a great reporter of how much donation of phosphine is giving when we have a bidentate phosphine and we can see the J values. So it's a really nice technique to understand how much donation is being given. And so we see that if we're going to form an arine requiring a lot of donation, then we're going to see these J values change a lot compared to when we don't have an arine. right? So we take our sigma aryl complex and we add in an activator. We use potassium pentoxide due to its solubility. And by the time you get down to the NMR room, something forms in 96% yield. So it's a very clean spectra. What formed? Our first clue was that we went from a J value in this sigma aryl complex here of about 25, and we can track that down all the way to a J value of about 4, meaning that these phosphines are now donating a massive amount of electron density into something. And of course, we're hoping that it's an arine. And so it took us a bit of time, but we were able to get the crystal structure and actually verify for the very first time access to what had been deemed an inaccessible arine. So we're super excited on this day to be able to study this complex and actually understand, the amount of back donation necessary to actually form this. So I'm going to talk a little bit about some of the structure of these, and that's important because it actually informs us a lot about reactivity. And then we'll talk a lot about the reactivity of these and what kind of coupling partners we can do, and the difunctionalizations that we can do on these molecules. So when we're taking a look at the crystal structure, as well as the computed values of what these inaccessible arines should be, I'll go ahead and bring in the cartoon here. And what we see here is the calculated value of that C1, C2 bond length is 1.256 angstroms. In the crystal structure, we see it elongated a ton. It's not so much so that it's a double bond as we see in the crystal structure of our sigma aryl here, but this gives us an idea that actually a lot more back donation is necessary to stabilize these arines than it is for what are deemed accessible arines like benzene. So we actually see an elongation of that bond compared to something like benzene or the accessible benzothiophene. So this tipped us off that actually this could have some really interesting reactivity that other metal-bound arines really haven't explored. So we can make a variety of these different structures with different functional groups on them, deprotectable groups. I mean, at this point, we changed the heterocyclic core a ton, but I'm just going to walk through some of the implications of the electronics of these. So we can get these crystal structures and we'll take a look at the bond lengths in comparison. So, why do we care about crystallography as organic chemists? Well, it turns out it's going to inform a ton about reactivity as well as about regioselectivity. Which termini of that arine bond are we going to react at? We can get a lot of that from structural studies. So sort of bringing in the cartoons here of the C1, C2 bond here, what we see is that looking at it across the electronic variation and steric variation, we really actually don't see that CC bond changing at all. So these are likely going to react all pretty similarly. But what we do see is a contraction when we start to change the linker length of our phosphine. So we can actually contract that bond a bit and make it more alkyne-like, which is going to be great for reactivity if you want this arine to behave like an alkyne. The other thing that we can note is that when we change the structure of our heterocycle, we do see a difference in that CC bond length. And that's going to have implications for reactivity. We've elongated it. It's less alkyne-like. The other thing I want to note, and these tiny differences in values may not be meaningful to you all, but really what we're going to look at next is the nickel C1 versus nickel C2 bond length. And so when we're thinking about regioselective reaction and metal arine reactions, it turns out it matters a ton because if you have a longer bond length, that's the termini of the arine that's going to react. So what we can do is we can see there's really not very much variation in those bond lengths when we have a 2-carbon linker. But if we want to get a regioselective reaction, we can just change the linker length of our ligand. And we can actually start to induce differences in that nickel C1 versus nickel C2 bond length. And so using this linker length, we can get a far more regioselective reaction. So this is why we care about the structure of these compounds as organic chemists, is both for reactivity as well as regioselectivity implications. So the phosphine values don't vary too much. We do see that the CF3 contracts that J value even more, and that makes sense. We're pulling more electron density out of those phosphines, and so that's a great readout for that. Okay, so this is a lot of organometallic chemistry, which really gets us excited. But why does the average organic chemist care about this? So if you're not a heterocycle chemist, I'm going to tell you that I don't think before starting this project, my group or I really appreciated how much it takes to build up libraries by just swapping out the scaffolds, right? So we can think about if, this was a drug molecule candidate and your warhead was maybe this blue bubble or this silver bubble. And what you wanted to do is you wanted to change out these scaffolds to understand different H-bond properties. You might want to consider different solubility. You might want to change out your heteroatom to understand the reactivity. What you would have to do is you would have to build up all of these structures from the individual components. All right. And so you see here that, one of your coupling partners is going to be a bromide. And then in the next molecule, if you want to just swap from imidazopyridine to indole, you'd have to build that into a ketone. If you wanted to switch to a pyrazine, then you'd have to switch to that coupling being in a nitrile, right? But if you had, a new functional group for 5-membered and heterocycles, then you could think about just making the arynes of each of these different heterocycle scaffolds and then having a common set of coupling partners. And this would really easily allow you to derivatize very quickly by swapping out that heterocycle core. So, a case study for this would be something like Ambien in the development. This is already commercially available. They're not going to redevelop this, but if you were developing this and you wanted to change out that heterocycle scaffold, you could do that in a single step by using an aryne intermediate instead of having to build up all of those individual molecules. So by swapping out the imidazopyridine scaffold core, if you wanted to swap out for indole, aza-indole, pyrrolopyrimidine, you could do that with these very easily commercially available reagents. And you could start to very easily derivatize this, right? So you can imagine, this is a functional group that was not accessible whatsoever to the medicinal chemists, but now we're bringing it to them to be able to very easily derivatize these molecules. But so that's sort of the utility. This is why we care about it as organic chemists, but that really doesn't tell you too much about the reactivity. So we can think about the organometallic aryne chemistry that's known in the literature and some surprises that we found along the way as well. And then organometallic sigma aerochemistry is well known, right? These intermediates are in cross-coupling reactions, amination reactions. This is well-developed chemistry that we can utilize for our second functionalization, right? But this is well-developed and well-known, so we're actually going to first focus on the organometallic chemistry of our first functionalization, how that aryne is going to react. So in the literature, free arynes that are not bound to metals are highly electrophilic, and it turns out late transition metal arynes are actually nucleophilic. All right, so they actually change the philicity of the functional group based on whether it's bound to a metal or not. Okay, so we can, if this is nucleophilic, that's what the literature says. We can react with an electrophile, fantastic. We get excellent yield, and in this case, it's very regioselective reaction, which is something that we're still focusing on figuring out. Of course, we will do a second functionalization on this molecule, but just to show we can work it up to show the regioisomer that we get. So, the nucleophilicity of metal aryne chemistry is well known. We can react with alkyl halides. We can react with things like aldehydes. We could react with iodoniums. Quite interestingly and surprisingly, this iodonium does not oxidize the nickel. Instead, this acts as a nucleophile and displaces this triplet. You can make new iodoniums. So the electrophilic coupling partners and the nucleophilic character of the aryne that's well known checks out in these systems. So that was quite exciting to us, but we had noticed those bond length differences and the nickel carbon length differences compared to other metal bound arynes. We thought to ourselves, maybe that has implications for reactivity. And it turns out that it does. These are well known to be nucleophiles, but it turns out that these are actually ambiphilic molecules and they are actually electrophilic as well. So we can actually return that aryne character to what we would consider with free arynes as electrophiles. So we can react with a nucleophile in this case instead of an electrophile. So the ambiphilic character is quite exciting, thinking about things like carbines, which we heard a lot about, and the wonderful reactivity that those have when they can do with different groups, they can be ambiphilic. You can see how useful that can be. So we can react with other nucleophiles, CSP3, hybridized carbon, CSP2, CSP. You'll note here it's kind of interesting that the regioselectivity starts to change based on the hybridization of the carbon. And that's something that we're trying to figure out right now. And we're quite excited to study why that is. So we're super excited that we have this ambiphilic molecule. All right, so now what can we do with that? And what are the implications of this ambiphilicity on difunctionalization reactions? So something that I'm super excited to share with you is if we treat this as an electrophile, this new sort of discovered or newly exploited reactivity of metal-bound arynes, and we react those with a nucleophile, and then we do normal or sort of well-established sigma aerochemistry, we can access this regioisomer of our molecule. But because these are ambiphilic, what if we switch the philicity of our coupling partner from a nucleophile into an electrophile? Well, it turns out if we did that, then we can actually just reverse the order of the addition of our reagents, and we can access the other regioisomer. So we're quite excited about this. You don't have to change your molecule at all. You don't have to change your ligand or anything like that to access the other regioisomer. You can just switch the order of addition of your reagents. And so we can think about this as being quite impactful. So those sort of libraries of different heterocycles we can swap out, and now we can provide access to both regioisomers for people to be able to screen in any sort of molecule libraries that they would want. So these heterocyclic arynes surprise us every day with their reactivity. So I showed you that iterative cross-coupling ability. We can think about the reacting with electrophiles. We could also think about oxidizing our nickel. Now that we're bound to nickel, we actually have more modes of reactivity. So we can think about fluorination and trifluoromethylation. We've been able to accomplish as well cyclization reactions as well. So we can form more annulated products through these methodologies. So they're electrophiles or nucleophiles as well as enophiles. And so that really opens up some of the chemistry for this. So that's where I'll wrap up. These precursors are incredibly easy to prepare. You can buy them in multi-grams from Ambead, do a single borylation reaction. We can just exploit simple organometallic principles and actually be able to access these inaccessible arynes. So we're just incredibly excited about the reactivity that we're discovering. And I didn't have time to talk about regioselectivity today. I gave you a couple of hints based on bond lengths, but we can actually start to develop models for regioselectivity. So with that, I'll go ahead and thank my group again. They're a really fantastic group of students and postdocs to work with. I highlighted those that worked on this project, but I certainly want to acknowledge all the hard work that everyone in my group does. So with that, I'll again thank the organizers for this incredible opportunity and be happy to answer any questions.
Courtney, that was fantastic. Thank you so much for sharing. We do have a couple of questions here. So the first one I have is from Dimitri, who is asking about the C1 versus C2 bond variations. Like, what would you say if you had different phosphines on the nickel? Is there some way to tweak that to allow the change in reactivity from one to the other?
Yeah, I love that question, and that's something that we're actively working on. So we use a lot of Fox ligands in our lab. So these C1 symmetric P versus N donors, and that certainly has a lot of implications. We can actually control regioselective addition trans to the phosphines. So we'd love to try those out. We also have a collaborator, Brian Nell at Ripon College. It's an undergraduate institution, and he's actually making these unsymmetrical phosphines that you're asking us about. So really fantastic question, and that is something we're actively looking into. And it turns out that you can affect the regioselectivity by changing, sort of having different donor strengths on that bidentate ligand. So really, really fantastic question.
Yeah, sorry about that. My mic was up over my ear because I was having lunch while you were talking, and I forgot to move
No
it.
worries.
So another question from Paul is, do acyl halides produce 3-acyl 2-halo indoles?
Great question. That's not something we have explored. I know we tried that in a single reaction. But that's something we would love to try. I would not be surprised if that's exactly what it produces. You can imagine that, a difunctionalization with a single reagent like that could be quite advantageous. So yeah, it's something we can absolutely consider, and we will likely try. Thank you for the question.
So I have one about not necessarily the regiochemistry, but when you're coming in with the different reagents, whether you showed the zincs or the trifluoromethyl cation, for instance, is there a possibility that you're, instead of maybe just a nucleophile, for instance, or are you getting a coordination to the metal and then a reductive elimination, or that kind of mechanism as well, or instead?
Yeah, that's a great question. So we're studying the mechanism of that, and that's actually what we originally thought. What we thought was our nucleophile, for example, was transmetallating to our metal and then doing a migratory insertion. But the more and more that we study, we actually think the arine is just sort of being attacked by the nucleophile, and it's actually placing whatever like zinc or magnesium or lithium on the other termini. So it's no longer bound to your nickel. So that's a relatively new discovery on our end. So as far as the electrophilic sources of CF3 and fluorine and things like that, you're spot on. That's what we're trying to get it to do. We're trying to get it to engage with a metal and oxidize the metal either through 1 electron pathways or 2 electron oxidative addition followed by reductive elimination. So this nickel is like quite electron poor because it's donating so much electron density to the arine. So that's another mechanism that may surprise us in how it reacts. But that's our current hypothesis, is that we'll oxidize the metal.
Okay, cool. And now we're starting to get a couple more questions pouring in here. I'm just going to ask a couple real quick because we're basically out of time at this point. But Anonymous, who asks a question every time, does this chemistry work with anything else on the nitrogen of the end of the heterocycle? Does it need a protected group at all?
Yeah, great question. So I will, so we show the benzyl group, which is, more deprotectable than methyl. And actually, excitingly, like we are now working on just the NH. And so we do have preliminary data that says that we can actually have no protecting group whatsoever. So that will be an exciting result that will come out hopefully relatively soon without any protecting group there.
Awesome. All right. Well, we're gonna end it right there. I really appreciate you coming in, and Huw, again, to you as well. Thank you both for a wonderful day of chemistry. Thank you to Alan and DJ for their wonderful work as always on behind the scenes. My new and hopefully future co-host Alex for his work today. Steve, as always, in the background and in the foreground, I should say. And he's gone though, so we'll just say thank you, Steve. And but everybody, wonderful day. Thank you so much, and we'll see you all